Hey, it's Tim, K5OHY. First, I want to thank all the new subscribers. This channel's seen some growth over the last couple months, and I really appreciate all the support. I've been posting videos for a while, but lately I've been diving into different ham radio topics, especially antennas, and approaching them not from an expert point of view, but more as someone who's learning along the way and then just sharing that process with you. Over the next couple of videos, I'm going to take a look at the end-fed half-wave antenna. This video is going to focus on building an inexpensive but yet efficient 49:1 UNUN and doing some testing with the NanoVNA to make sure it works and to check the efficiency. The next video, I think it'd be interesting to take a look at the different ways to deploy this antenna. There are a variety of configurations: sloper, inverted L, inverted V, vertical, etc. So I'll take a look at the computer modeling for each configuration on a few different bands. Then finally, I'll take this antenna out for parks on the air activation to see how well it works on the air. The end-fed half-wave antenna is one of the most popular antennas for a variety of reasons. First of all, it's very simple. It's an impedance transformer, like a 49:1 UNUN, a single radiating wire, and then either a short counterpoise, or a lot of people use the coax as the counterpoise. Having the feed point at the end of the antenna makes it very easy and simple to deploy. This antenna is also resonant on multiple HF bands. For example, if you cut a 40-meter half-wave piece of wire, which is about 66 feet long, you're going to get a resonant antenna on 40 meters, 20 meters, 15 meters, and 10 meters. Like many new hams, this was my first antenna when I got back into the hobby. And I use it for everything, both here at the house and for my parks on the air activations. So there are a lot of commercially available end-fed half-wave antennas, and they're not really expensive. You can get a complete antenna for about $75 to a little over $100. However, after building a few impedance transformers, I've realized how easy and inexpensive it can be. Plus, I find it more satisfying to build your own antenna and then use that to make contacts. In fact, that's probably one of the most rewarding parts of this hobby. Plus, if you build your own transformer, you can kind of tailor it to your needs. For example, maybe you're a QRPer and you need something that can handle 5, 10, or even 15 watts and have a small, lightweight transformer to use out in the field. Or maybe you want to build something that can handle a kilowatt. Either way, you can design the transformer for your specific needs. Over the last year, I've actually kind of avoided end-fed half-waves. I had come to the conclusion that they weren't the most efficient antenna. And while that is true for the typical 49:1 UNUN, they're only about 70 to 80% efficient, which means you lose about 20 to 30% of your power. If you transmit 100 watts, you may be only radiating 70 or 80 watts. But after doing a little bit of research, I've ran across a method of winding a transformer that's more efficient. In fact, if you haven't seen Colin, MM0OPX, and his YouTube channel, he has done extensive testing on not only different windings, but different toroids. And he's come up with a 49:1 that's approximately 90% efficient. So that's the transformer that I'm going to try to build in this video. So before we get in the build, I think it's important to kind of visualize and understand the difference between the different types of transformers and how they're built. So this is a simple schematic of an UNUN. And as you can see, there are two windings in series. You have a primary and secondary. The most common way to wind a 49:1 is 2 primary turns with 14 secondary turns. And then if you take 14 over 2 and simplify that fraction, that's going to give you 7:1, and that's going to be your turn ratio. If you take the turn ratio and square it, that gives you the impedance ratio. So 7:1 squared is going to give you 49:1 impedance ratio. Another example is if you add one more turn to the secondary, so 2 turns on the primary, 15 turns on the secondary, that simplifies to a 7.5:1 turn ratio. That's going to give you a 56:1 impedance ratio. And then one final example. When I built a 4:1 UNUN for my budget Challenger build, it had 8 primary turns, 16 secondary turns, So a 2-to-1 turn ratio squared, that's where you get 4-to-1. So let's go over briefly the use case for each type of UNUN. If you can picture a half-wave length piece of wire and the feed point's in the middle, like a dipole, the impedance is close enough to the 50 ohms your radio is expecting that you don't need any type of transformer, although a 1-to-1 balance is often recommended. If you move that feed point one way or the other, the impedance is going to rise. So if you go down to an off-center fed dipole, the impedance is around 200 ohms at the feed point. So if you take 200 and divide it by 50, you get 4. So a 4-to-1 UNUN is used for an off-center fed dipole. Now if you move that feed point all the way to the very end, you're going to get a very high impedance, a couple thousand ohms. So this is where you use a 49-to-1 or 56-to-1. So if you take 2,450 and divide it by 50, that's going to give you 49. So that's where you get your 49-to-1 UNUN. Okay, so let's talk about what you're going to need to build a 49-to-1 UNUN. First of all, you're going to need a toroid. So as you can see here, I've got 3 different toroids. These are all mix 43. This is an FT140-43. This is an FT240-43. These are very traditional toroids to wind a 49-to-1. However, the efficiency is not going to be quite as good. These are the type that will give you about 70 to 80% efficiency. This right here is a toroid that Colin, MM0OPX, recommends on his channel after doing a lot of research and testing. So this is a 264-325-1002, and I will link this in the description. They're about $8 or $9, so they're not very expensive, but it can handle 100 watts digital and maybe up to 200 watts single sideband. So it can definitely handle what most people are going to be running. Now he also recommends a similar thicker toroid for QRP work, and I'll link that in the description too. The next thing you're going to need is magnet wire. This is 18 gauge enamel magnet wire, and we're going to need about 3 or 4 feet of this. And finally, we're going to need a capacitor. Now, a capacitor is used on an end-fed half-wave transformer to try to take care of some stray inductance on the higher frequencies, and so it helps flatten out the SWR on 15 and 10 meters. And I'll try to show you that here in a little bit when we do some testing with the NanoVNA. Now, you'll also need a few other parts that I'm not going to get into because everybody's going to want to build these a little bit different. You'll need a coax connection, an SO239, or maybe a BNC connection, and some miscellaneous hardware. And then of course you'll need a way to mount this. All right, so let's get into the build. The first thing I'm going to do is cut some magnet wire, and you're going to need a few feet of this. I'm going to measure out, just kind of eyeball, about 45 to 50 inches of wire. So we're just going to go and then I'm going to go ahead and cut that. And then I'm going to cut off about 4 inches of this, 4 or 5 inches, and this is going to be our tap. And you'll understand that here more in a second. So basically how this works is you're going to have 2 windings of the toroid, and then you're going to have your tap, and that's going to be the center coax connection. What I found is it's easier to solder the tap on before you start winding. So what I'm going to do is I'm going to measure out about 8 inches from the end, and I'm going to scrape off the enamel right there, and then we're going to solder the tap on. So there's different ways to get the enamel off. I use a razor blade, but you can use sandpaper or a knife, anything that'll get the enamel off. But it's very important that you get all the enamel off or the solder is not going to stick. So as you can see here, I've got most of the enamel off right there. Now I'm going to scrape off the enamel on the end of the tap, and then we'll solder that. All right, as you can see, I've got the enamel off of the end of the tap. So now we're going to solder the two together. So what I'm going to do is I'm going to go ahead and just make kind of a bend in this wire, and then we'll just kind of clamp that on to the main wire. And what we'll do is just kind of hook it where I scraped off the enamel, and we'll just kind of clamp it on there. All right, so as you can see, we've got that on there pretty good. And now we're just going to go ahead and solder that together. And I'm going to use my little soldering iron here. I tend to overdo it with a solder, so usually I have to take some solder off after, but just want to make sure we get a good connection here. All right, let's take a look at that. Looks pretty good. I might just put a little bit of solder on the back portion here. All right, that looks pretty good. All right, so now that we have our tap soldered on, we can go ahead and start winding this. Now, how this is going to work is we're going to put the tap in the middle, and then we're going to wind 2 turns one direction, and then the other side is going to be the remaining 12 turns for a total of 14 turns. And each turn is 1 pass through. Now I found that this toroid is a little bit more difficult to wind because of the thickness. So on the inside, the wires are going to be like really close, and on the outside they're going to be further apart just because of the shape of this toroid. And so you kind of have to watch out to make sure they don't overlap in the middle. And I try to get this as tight as possible, but sometimes it's kind of hard. So there is... Oh, see what I did right there? I went through the other one. Okay, so we can try to make this look a little bit more pretty here. Okay, so now what we're going to do is take the other side, and we're going to go ahead and wrap 12 more turns. And as you can see, we have 1 turn, 2 turn, then the tap, and then we'll have 12 turns on the other side. So I'm going to go ahead and do that. So that is 1. And try to get these as tight as possible, but it's not real easy to do. This is 2. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have our toroid wound. Let me make sure we have the correct number of turns. So we have 1, 2, then our tap, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 total turns, 2 turns, and then the tap. So we're pretty much done building the 49-to-1. So now we're just going to hook it up to the NanoVNA and test it. Now, I don't have the capacitor on here yet. I'm going to hook it up to the NanoVNA and show you the difference between having the capacitor and not having the capacitor, so you kind of see what it does. I will put some zip ties on here to just kind of hold the winding where it is. So I'm just going to go around the ends here. What that'll do is just prevent it from unwinding. And you can kind of make it look pretty if you want. Mine usually don't look great, but they seem to work okay. And then we'll take another zip tie here and put it around the other side. Okay, so now what we need to do is I'm going to go ahead and cut the leads to about the same length, a couple inches. And when we put this in an enclosure, we may cut them even shorter, but I'm going to leave them just a little bit longer for now. So now I'm going to go ahead and scrape the enamel off the ends of each of the leads. And again, just to help visualize this, this is going to be our ground connection. After 2 turns, our center of our coax, and this is going to be our antenna connection. So let's go ahead and scrape the enamel off each of the ends. Okay, I've got the enamel scraped off all the ends. So now we're going to go ahead and test this with the NanoVNA. Okay, so I've got the UNUN hooked to my NanoVNA, which is hooked to NanoVNA Saver. And if you can see here, between the antenna lead and the ground, I've got 2 resistors. Now I bought, I think, 2400 ohm resistors, and then I added 100 ohm. And so when I measured this, it was about 2,468 ohms. So it's not quite 2,450, but it should be close enough to see if the UNUN is working. And so what I'm going to do here is I'm going to run a sweep on NanoVNA Saver. Now what you do notice is I don't have the capacitor installed. And so I'm going to take a screenshot here, and you'll be able to see that at lower frequencies, the SWR is quite low. In fact, at 3.8 megahertz, it's 1.17. However, in the middle of the 10 meter band, the SWR has climbed to to 3.8. So I believe that's the stray inductance causing that. So I'm going to go ahead and take a screenshot of this, and then I'll hook up the capacitor and we'll see what it looks like. All right, so now I've got the capacitor hooked in between the ground and the center of the coax connection, and I've run another sweep, and it looks much better on the higher frequencies. As you can tell, the lower frequencies are still really good, with 80 meters being at 1.0 SWR, and then up on 10 meters, it's around 1.5 to 1. So the capacitor definitely helps on the higher frequencies. So as you can see here, I've got two 49-to-1 UNUNs wired in the back-to-back method. So basically the antenna connections are connected together, and then I've got one plugged into the S11 port and one plugged into the S21 port. And how this works is we're basically going to send a signal from this port that goes through this UNUN, and then it goes through this UNUN, and then we're going to measure the loss on this port. So it's the S21 gain. So I'm going to go ahead and run a sweep of that. And what I'm going to do is take the gain on each different ham band, plug it into a spreadsheet that will then take that, divide it in two, because we have two UNUNs. The loss is for both of them, so it's going to be half of that value. And then that's going to convert that into a percentage of efficiency. So I'm going to go ahead and plug those values in my spreadsheet, and I'll share a screenshot with you. Okay, so I just plugged everything in the spreadsheet, and it looks pretty good. As you can see, we're around 90% efficient. As we go up in frequency, it does drop off a little bit, but still in 10 meters, it's around 87% efficient at the beginning of the band. So I'm pretty happy with those results. I think this is a very efficient 49-to-1, and it should work out pretty well. So what I'm going to do now is I'm going to go ahead and put one of these in an enclosure, probably a 3D printed winder, and then I'll be back with you and show you how I did that. So I just finished the 49-to-1 UNUN build, and what I did is I installed it in a 3D printed enclosure, which is also a wire winder. Let me show you that. So this is a model from KR1 BBT, and I've used his models for some of my other projects, and they're really well thought out. And yes, I know it's shaped like a frog, and you can even put googly eyes here if you want. But this model in particular is pretty neat because he has different trays for different size toroids, and you can screw it on the bottom and the toroid fits in there perfectly. It's a little bit tight to make your connections, but with a little patience, it wasn't too bad. So basically I have the ground counterpoise wire going first to the counterpoise lug, and then that also goes to the ground on the SO239. And then after 2 turns is our center tap, which goes to the center of the coax connection. And then you have the rest of the turns, so 14 total. And then this is your antenna connection. So this will be the radiating element. And then you can see I have the capacitor installed, and that goes from the center of the coax connection to the ground lug. And I read that you want to keep this, the leads on that capacitor fairly short. I'm not sure exactly why, but I think they said it can add some inductance. I'm not sure, but I kept them fairly short. So I look forward to taking this out and trying it out. If you want to use another model, the Ham Radio Dude has a couple really nice 3D printed models that he shares for free. And he also sells them on his Etsy. And I have no affiliation with him, but it seems like he does a really good job printing them, and he prints them in ASA plastic. And if you know anything about 3D printing, that's a very good plastic. It's very durable and it's very UV resistant. This model here, he designed to specifically use this little enclosure you can get on Amazon. And it's a really nice enclosure. I believe it's ABS plastic. And then it has a lid with a seal, and you can see the lid has threaded inserts. So you can basically screw this onto the antenna winder and have a fairly durable antenna. And then he's got just a antenna winder here that you can put your coax connection, your SO239 here. He also has a model that uses a BNC connection. So you can basically just mount the toroid on here, make your connections, and then maybe use some shrink wrap just to protect it. So either way it works. If you're making an UNUN for a long-term installation, you may want to get a more durable like junction box or something like that. But these 3D printed models should work out well for me. So that's it for this video. I'm looking forward to taking this out and trying it out. In my next video, I plan on looking at the radiation patterns and the computer modeling for a few different configurations and ways to deploy an infed half-wave. I'll look at a vertical versus a sloper, inverted L and inverted V, and maybe a few other configurations if I can think of any additional ones. But I'll basically plug that into computer modeling, and we'll see the radiation patterns on each configuration, and then we'll look at the different bands and how it looks on different bands. If you like this kind of video, make sure to subscribe or leave me a comment. 73.